Okay, so we're done with EIGRP as our routing protocol at this point, but if you are a true CCNA, you should also be able to work with OSPF. And so that's what we're going to move into next, is working with and manipulating the open shortest path first routing protocol and getting some experience with that. So let's take a look at our objectives for this section. On every device, except for switch 1, revert back to the configuration file you previously saved called pre-EIGRP. Or if you didn't save that for some reason, basically just remove all of your EIGRP stuff. So let's go ahead and do that real quickly. So we'll start with switch 2. We'll do directory flash just to make sure that it still has the pre-EIGRP in it. There it is. So now I'm going to use the config replace command. This is not actually a command that you learned at the CCNA level, but it's an awesome command where you can take a config that was previously saved somewhere else, like in Flash. And what this does is it, like it says, it replaces your running config. A lot of times when you for example, copy and paste something into your running config, it just adds to your running config to what was already there. But config replace actually completely removes your existing running config and replaces it with the one that you're loading. So that'll get us right back to the state we were at before I configured all of my EIGRP stuff and my delay and all that good stuff. It says, are you sure you want to do this? Yes. So let's just go through each device and do this. And you can see here this is much faster than trying to manually strip out all of my EIGRP related things. Now the one thing I probably want to do, because one thing this is also stripping out, is probably my frame relay maps that I created with my link local addresses. So I'm going to need to most likely reconfigure those. So unfortunately I did not save that. So let's just go ahead and do it quickly here, recreate what I did before. Yeah, I got rid of those, so I got to put those back in there. And this is going to be important to add this back in here, because just like with EIGRP, how it forms neighbor relationships using link local addresses, well, OSPF does the exact same thing. So for R1, we'll have frame-relay map IPv6, and we'll say R3 link local, and that's going to be 1 to 3 is going to be 131. And this is going to be R4 R4 link local, which is going to be 141. He's going to be talking to R1, so going to R3, he's going to be 341. Going to R1, he's going to be 141. Okay, that looks good. And lastly, R3s. R3 is going to be talking to R1 across 131 and R4 across 341. Okay, now I just got to put these in here. So R1, R3, and R4. Okay, so I'm currently in R3 already, so let's go ahead and do this one. Interface serial 000.134. And while I'm here, well, we'll come back to that. Okay, let's go back to router 1. And lastly, router 4. Okay, so now what I'm going to do here is I'm going to copy this back in. Copy, run to flash pre-EIGRP. This time I'm copying those link local ones as well, so I won't lose them. Yes, I do want to overwrite. Okay, that's R4. Here's R3 and R1. Okay, so we are now, you know what, let's go ahead and save this guy. Okay, so we just did that. Now let's go into OSPF. Configure all devices in this lab except switch 1 for OSPF for V4 and V6, adhering to the following guidelines. So there's actually several sets of guidelines here, so as I go through this, I would recommend you take a screenshot of this so that when I go into the next page that has more guidelines, you can still remember this initial set. So router ID is basically going to be the same thing as what we did with EIGRP. We're going to use, once again, specific network statements. Okay, we got that. All links connecting to subnets A through G should be placed into the OSPF backbone area. Okay, so here's A through G. So the OSPF backbone area, otherwise known as area what? That's right, area 0. So everything here that I've drawn in this yellow circle is going to be in area 0, all those links. And all links connecting to subnets H through subnet Y should be placed in area 1. Okay, let's keep going. IP version 4 OSPF security should be implemented on all devices using a password of INE. Plain text passwords must not be exchanged. Ensure subnets assigned to loopback interfaces are advertised in LSAs with the configured subnet mask. So let's stop right there. Letter F. what do we need to do? First of all, why do you think letter F is even in there? I mean, if we just enabled via a network statement OSPF on a loopback, if that loopback is configured as a /27 or a /29, won't the LSA that advertises that loopback by default go out with /27 or /29? I mean, why do we even need objective F there? Any ideas? The reason why we need that is because when OSPF recognizes that's been configured on a loopback interface, it actually classifies it as a loopback, which means regardless of what the mask is, it will advertise it as a /32 as a host route. It won't advertise the actual network that you've configured on it. That's the default behavior. So objective F is saying we want to prevent the default behavior and instead configure a command so that it actually advertises the network mask as you've configured it. So what's the command to do that? So the command would be on the actual interface itself, IP OSPF network point to point. So instead of having OSPF viewed as a loopback, we want to view it as a point-to-point network. And that will allow it to pick up the actual mask. Prevent OSPF hellos from being generated on loopback interfaces. Well, if you've already done the EIGRP section of this lab, you know that what that's referring to is passive interfaces. Once again, making those loopbacks passive. When completed, R2 should be able to V4, V6 ping any of the IP addresses on R3 and R1's loopback interfaces. And lastly, ensure that router 2 can still ping the loopbacks of router 3, even if links connecting to subnet, it's got to be I, subnet I, are disabled. Okay, so we'll get back to I here, but the first A through H objectives are pretty clear. Really, the only thing that we're doing sort of out of the ordinary is that network point-to-point on the loopbacks, and then we're implementing OSPF authentication. Okay, so let's go ahead and start working up our configurations for this. All right, so we will start with router 2 on the far side and just work left to right. So in router 2, we're going to type router OSPF, and we'll just give it some process ID, doesn't really matter. And then we're going to have router -ID like that. And then we're going to give it some network statements. So network, actually what I can do here, hopefully I saved this. If I still have my EIGRP config, I can use the exact same network statements. Oh, look at that, beautiful. Boink. Okay, that'll make things a lot easier. So with our EIGRP configs, we included every single network. We made the loopbacks passive, and we included wildcard masks, so I can use most of this stuff all over again. So we'll just do that. Router OSPF 1. Okay. Okay, that takes care of that. And now we're going to just get rid of the EIGRP portion. Keep the router ID the same. The network is fine. So here on switch 2, all of his interfaces are in area 0. So let's just go ahead and add that. And then we'll come back to him. Switch 3, all of his interfaces are in area 0. Okay. Router 1, all of his interfaces are in area 1. Okay. And router 2, all of his interfaces are in area 0. Okay. And router 3, all of his interfaces are in area 1. Okay. And router 4, he's the only guy who is right in the middle. So let me ask you this question. Router 4, because he has some interfaces in area 0 and some interfaces in area 1, that makes him a very special kind of OSPF router. What is he going to be? What role is he going to take? That's right, Abu Bakr. He's going to be an area border router. Exactly. All right, so let's just go ahead and put my commands on here, and then I'll change the areas as needed. All right, so let's see. So dot 48 is going to be in area 0, and dot 24 will be in area 0. All right, that looks good there. Okay, great. So we've got the router IDs, we've got the OSPF process, we've got the correct network statements. For those routers that have loopbacks, we already have passive interface commands. Great. So we can get rid of. Now for the IPv6, same thing. IPv6 router OSPF1. The only reason we have to create the IPv6 process for OSPF is because, once again, we want to change the router ID. Oh, and also make loopbacks passive. Okay. And I don't have to make the IPv6 router process OSPF1. I'm just doing copy and paste here, but the IPv4 OSPF process and the IPv6 OSPF process are completely unique, independent processes. One could be process 1, the other could be process 99. So they don't have to match, even though in my particular example here they are matching. Okay, so let's scroll back up and see what else I need to do here to create this config. Let's see here. So I've got the IPv6 process, so now what I need to do is go onto the interfaces and enable my IPv6 OSPF, IPv6 OSPF 1, and here's where I specify the area as well. So this is switch 2, so he's going to be in area 0. IPv6 OSPF 1, area 0. And also that other VLAN is going to be there. Okay, great. Switch 3, all of his interfaces will also be in area 0. It's also good that I'm doing it this way because here you get to see a real good contrast between the EIGRP and the OSPF configs, and you can see how very similar they are in many cases. Okay, I'm going to have to go back and make my loopbacks passive in IPv6. Oh, I've just been sort of blindly doing this. I haven't been thinking about it. Off in La La Land. Okay, I haven't been paying attention to my area. Switch 2, yes, all of his interfaces are in area 0. Switch 3, all of his interfaces are in area 0. Okay, router 1, yeah, that's where I made a mistake. So router 1, all of his interfaces are in area 1. Great. Router 2, all of his interfaces are in area 0. Okay, so we can keep copying and pasting there. Oops. Router 3, all of his interfaces are in area 1. Router 4, he is my area border router. So serial 1/0, that's in area 1. Serial 1/3, that's also in area 1. And my 2 fast Ethernets are in area 0. Actually, my virtual template is in area 0. Okay, I think I missed the loopbacks on one of these routers. Let's see here. I think I missed on router 1. I think I forgot to put his loopbacks into OSPF. Yep, I did. Okay, so router 1, his loopbacks are in area 1. Okay, and I want to make sure I do passive interface on these routers. So this guy right here, have him do passive interface. Okay, and let's go back to router 3 and do passive interface for him. And router 2, make sure that he's got a passive interface command. Yes, so 2, 3, and what about 1? Is this router 1? Yes. Okay, so at this point, I'm almost done. I've created an IPv4 OSPF process with the correct router IDs and network statements. And for those devices that have loopbacks, I've made those loopbacks passive. I've also created an IPv6 router OSPF instance by enabling it on all the interfaces, creating the correct router ID, and making passive interfaces of my various loopbacks. So the only thing I have to do at this point is my authentication. Now, like I mentioned earlier, if we go into one of these routers, I'll just pick whichever one I happen to be in at the time. That's router 1. If I choose, for example, my point-to-point interface, serial 1/3, IP OSPF authentication, you can see here some message digest. That's what we're going to want to do. But in addition to that, see, this is the one thing that's different. Like I'd mentioned, with EIGRP, we put our authentication key within a keychain. But here for OSPF, we don't have that choice. We have to have our key right on the interface. So based on that, I'm going to delete all my keychains because those are no longer relevant for OSPF. Last one here. Great. Okay, and now I got to modify my interface level commands. We see it's IP OSPF authentication, and we were explicitly told in the objectives right here that OSPF security should not use plain text passwords. So we have to use MD5 in order to meet that criteria. And that is the IP OSPF authentication message-digest. So start up here, IP OSPF authentication message-digest. And we are told to use a password of INE all uppercase, okay? And that is the IP OSPF authentication-key, and then the password. All right. Now, the instruction said just do that for IP version 4, and that's because for IP version 6, we'd have to implement IPsec. With IP version 6, in order to get authentication, it's not as easy as just doing a couple of interface commands. You got to configure all this IPsec gobbledygook, and we don't have to worry about that for the CCNA, so I will just get rid of this. Okay, so this is just what I'm going to copy and paste, and that should finish everything off. Don't have to do any authentication on my loopbacks because there's no OSPF peer that I'm going to be talking to on the loopbacks. Actually, there is one more thing I'm going to need to do to get this working. And I'm going to see if you guys can spot it. Okay, that should do it. So my routers and layer 3 switches should now be ready for me to paste in my OSPF configurations. Are there any questions about what I did before I start copying and pasting these into my devices? I didn't put my, I didn't make my loopbacks point to point. Without doing that, they'll just be advertised as /32s. And that command is IP OSPF network point to point. And I think you can even do that with IPv6 as well. Yep. Okay, so let's just copy this in to those various devices that have loopbacks. There we go. Let's see, those are my routers. Router 1 has some loopbacks. Where are you? Right? I guess I didn't include my loopbacks in here. Did I delete that? I made them passive, but I don't see the loopbacks. Okay, I'll come back to that. Router 2 has some loopbacks. 3 has some loopbacks. Okay, and now I should just be able to copy this directly back into the router where the loopbacks just vanished for some reason, which was router 1. Okay, so that looks good. Let's save that before I lose all my work. All right. So we've got here, I think everything's good to go. Now, there is one thing I know that's missing, but I'm going to see if you guys can spot that before I put this in here. But everything else I believe is okay. I've got OSPF on all my interfaces. I've got authentication on all of my relevant interfaces for V6 and V4, well, not V6, but for V4. All right, let's just start copying and pasting. Enough of the verification. Let's get cracking. All right, starting left to right, let's do switch 2. Oops, that didn't work. Okay, no error messages, good. So that works. Let's go to switch 3. And as soon as I do this, switch 2 and switch 3 should form both V4 and V6 OSPF adjacencies between them. Okay. Okay, so we see here OSPF adjacency change. So that is my V4 process. Just formed a neighbor relationship. Now, where is my V6 neighbor relationship? Show IPv6 OSPF neighbor. Okay, they recognize each other. They're just taking a little bit longer. All right, I'm not going to wait. Let's just keep moving on here. So let's now go to router 1. Just going up the keyboard here. That's right. A couple of my loopbacks don't have IPv6 addresses on them. That's fine. Doesn't hurt to do that. All right. Now let's go to router 2. Okay, that looks good. So here my OSPF v3, that's my IPv6 OSPF. So I'm seeing both adjacency changes on v3 and OSPF for IPv4. That looks good. We'll keep going, then we'll come back and verify that all of my neighbor relationships are working. Well, some of them won't. I know for a fact that some of them are not going to work. And we'll see if you guys can figure out why. Let's see here. So R3. And lastly, R4. Okay, so let's move left to right. Let's go all the way back over to R2 on the far left of my topology and just start verifying our expected neighbor relation. So let's start with IP version 4. Show IP OSPF neighbor. And how many OSPF neighbors would we expect to see on router 2 from an IP version 4 perspective? I believe we should have a neighbor relationship with switch 3 across here, a neighbor relationship with switch 3 across here, and a neighbor relationship with router 4 across here. So yep, we should have 3 neighbor relationships. And we do. Now, this is interesting. 4, so this is router 4 across my PPP over Ethernet connection, is in the exchange state. Normally that's not necessarily a bad thing unless it gets stuck there. It shouldn't be there for very long. And the fact that it's here as long as it is a little concerning. And I think I know why. Now this is not something, I don't think, actually this might be something that you, well here, I'm going to answer that question myself. So let's go to the CCNA blueprint. Look under OSPF to see exactly what they expect you to know. All right, here's our OSPF section right here. Okay, configure V2, V3, router IDs, passive interface, discuss multi-area, understand LSA types. Okay, so that's configure and verify. And then under troubleshooting, here's what they expect you to know as far as troubleshooting is concerned. So, that's what we're doing right now. We're troubleshooting. We're trying to figure out why router 2 and router 4 are stuck in the exchange state and they are not forming a neighbor relationship. So, based off of what you should know, if you watched all the videos and read all the books, what do you think could possibly be the problem here between router 2 and router 4? I'll even do this for you. I'll even put into the downloads section, or I should say the file section, that configuration file I just worked up. There you go, ospfconfigs.txt. Go ahead and reload your browser, check the file section, and you'll have that ospfconfigs text file I just created. Take a moment to look at that. See if you can spot anything in there that might be causing, yeah, look at this, too many retransmits. Definitely something going on between these guys. What ideas do you have? I'll tell you, it's not going to be an authentication issue, because if it was an authentication issue where they were using the wrong type of authentication, they were mismatched, or their passwords were mismatched, they would never even get to the exchange state. They would ignore each other's hellos because the authentication information is right there in the in the OSPF header. And so they wouldn't even see each other. So authentication is fine. It's not that. Clearly my network statements are fine because they're seeing each other. They're exchanging hellos across the correct network. This is kind of a tricky problem. Give you a few more seconds to give me any answers that you might have. Well, I believe this is an MTU problem. And this is one of the things on the CCNA troubleshooting they want you to know about MTU. Because a mismatch in MTU is not detected in the exchange of hellos, because hellos don't contain that information. It's only until you start exchanging what's called database descriptor packets, and you do that when you get to the exchange and extart stages. That's when you can first detect that your neighbor's MTU is not the same as your own. So let's see if we can verify that. On R2, the interface that he uses to get to his neighbor is dialer 1. So show interface dialer 1. And that shows on here that we have, let's see here, where is that MTU? Where is the MTU? Somewhere in here. All right, here, 1500 bytes. Okay, 1500 bytes. Let's compare that with router 4. Now router 4 is not using a dialer interface, he's using that virtual template. Show interface virtual-template 1. Okay, this says 1500 here, but I think it's actually, it might not be the virtual template that we need to look at. Show IP interface brief. Let's see. I think we need to look at this virtual access interface. Show interface virtual-access 1.1. Yeah, see, here's the mismatch. 1492. So we've got 1500 on one side, the dialer interface, and we've got 1492 over here on the virtual access interface. And that is causing our mismatch. And that's why these guys can't get fully adjacent with each other. So what we need to do is 1492 is actually appropriate because with PPP over Ethernet, you can't send a 1500 byte. If I had a 1500 byte packet, normally that would be perfectly fine to put inside of an Ethernet frame. Ethernet would add an extra, like, I don't know, 12 to 18 bytes, something like that, and it would be just right to reach the maximum size Ethernet frame. But when I'm doing PPP over Ethernet, if I take that 1500 byte packet and then wrap it inside of PPP, well, PPP adds an extra 8 bytes of overhead. And so now if I try to put that into an Ethernet frame, the frame will be too large. It'll exceed the maximum size. So that's why this is doing 1492. And I think the reason why this is doing 14, you might be thinking, well, why isn't the other side 1492? I mean, they're both PPP over Ethernet. Weren't they both smart enough to do that? Well, I think here's the reason. This is the only thing I can think of. If I do a show run here, remember that virtual access interface was created dynamically as a result of this virtual template. And the virtual template is being used by the BBA-group, which says PPP over Ethernet. So because the BBA group knows he's doing PPP over Ethernet, he relays that information to the virtual template, and then when the virtual template spawns or creates the virtual access interface, he's smart enough to say, hey, look, you need to have a maximum MTU of 1492, so we don't get too big here. But if we go over to the other side, router 2, right over here, his dialer interface knows that he's doing PPP, but there's nothing telling the dialer interface, hey, by the way, this PPP you're doing, that's going to be wrapped inside of Ethernet. The fast Ethernet interface knows that because he says PPP over Ethernet, but this is a child of the dialer interface. So, on the PPP over Ethernet server, the virtual template, you can sort of think of it like this. The virtual template was looking up at the BBA group, and the BBA group was saying, okay, virtual template, you're going to be doing PPP over Ethernet. But here on the client side, the dialer interface has nothing to look up to. There's a child beneath him, a fast Ethernet interface, but there's nothing on top of him saying, okay, dialer interface, we're using you for the purposes of PPP over Ethernet. So that's why the dialer interface has this mismatch. I believe that's what's going on. So what we need to do is we need to change the MTU of the dialer interface to match the other side. And that should resolve our problems. Interface dialer 1, 1492. Now if that works, there we go. That's what I was hoping to see. Our IP version 4 OSPF process just formed a neighbor across that PPP over Ethernet connection. Now, I'm not sure why IPv6 hasn't formed a neighbor relationship yet, but we'll come back to that. We'll get back to that. So now if I do show IP OSPF neighbor, there we go. Now I've got 3 neighbors in the full state. That's what I expected to see. So let's keep moving on with switch 2. He should only have a single neighbor. Yep, he does in the full state. Switch 3. Switch 3 should have, let's see here, let's count them up. He should have a neighbor on subnet C, subnet D, subnet G, and subnet E. And yes, he does. He's got 4 neighbors. All right, router 4. Show IP OSPF neighbor. Now before I hit the enter key here, how many OSPF neighbors do you think router 4 should have? Well, if we go back to this, router 4 should have a neighbor with 3. He should have a neighbor with router 2. He should have a neighbor across the frame relay with router 3, a neighbor across the frame relay with router 1, and a neighbor across the PPP connection with router 1. So he should have a total of 5 OSPF neighbors. Let's see if he does. Uh-oh! We've only got 3. Actually, I expected this. Now, you've got the configuration files there. I sent them to you as text files. Why? And we can see here what's missing. He's missing his OSPF neighbors across subnet H, across that frame relay cloud connecting to 3 and 1, otherwise known as serial 1/0. Why doesn't he have those? What did we do wrong? Okay, so Dwayne has an idea, thinking that maybe we should change the OSPF network type to broadcast. Okay, that would work. That would work. Any other ideas of anything else we could do to get this to work, other than changing the network type? What's the network type right now? By default, what's the network type that router 4 is seeing on serial 1/0? That's right, non-broadcast multi-access. How would I view that? What command could I type in to verify that? Well, someone says show IP protocol. No, show IP protocol won't show that. Won't show me that. That's right. I need to type in show IP OSPF interface and specify the interface I'm interested in. Show IP OSPF interface serial 1/0. And right there it says network type non-broadcast. Okay, so one alternative idea was to change that network type into broadcast, and I asked you, okay, is there anything else we could do other than that? Anything else we could do? Well, the other thing we could do is statically configure some OSPF neighbors. And the CCNA would definitely expect you to know under what circumstances you would need to do that and how to do that. And this is a prime example of that. Whenever you have a network type of non-broadcast, you're not going to dynamically form a neighbor relationship across that kind of a network. So you have two options. Either change the network type to something else, if it's appropriate, or statically configure some neighbors. So let's go ahead and do that. Router OSPF1, neighbor 190.190.9.34, that's router 3. And before I hit the enter key, another question. Since I'm choosing to use this method of using static neighbor assignments, do you think I need to do this on all three of these routers, routers 1, 3, and 4, pointing at each other? Or do you think just doing it on router 4 will be enough? Well, what should happen, I mean, to have a nice, elegant, clean config, it would be a good idea to do it on all of them. But in reality, I should only have to do it on, well, if I do it just on router 4, then that should be good enough for him to form a neighbor relationship with routers 3 and 1. Now, 3 and 1 won't form any neighbor relationships with each other, but this should be enough to kickstart the process. Now it's not, actually there it is. Look how fast that was. So my neighbor relationships went up. Okay, so to get 3 and 1 to recognize each other, I have to choose one of them. I'll just go to router 1. And I'll configure a neighbor statement on him, just pointing to router 3. Make sure we can ping that neighbor. We should be able to. Okay, just taking a little bit longer. There it is, just came up. Okay, so now if we go back to router 4, he should have all 5 neighbor relationships. Yep, he does. And if I go to router 3, he should have 1 relationship with router 4 and 2 neighbor relationships with router 1. So I should have 3. And I do. So at this point, from an IP version 4 perspective, I should have end-to-end connectivity. So if I go back to router 2, show IP route OSPF, let's just see if we've got everything in here. This is primarily what I'm looking for. I'm looking for the loopbacks of router 3 and router 1 on the far end of the topology, and there they are. There's the loopbacks of routers 3 and 1. Yep, 22 subnets. Okay, now I saw a problem between router 2 and router 4 over that PPP over Ethernet connection for my IPv6 process. Probably the same thing, probably an MTU, because remember, I did the IP MTU command. That only affects IP version 4, doesn't affect IP version 6. So actually, let's show IPv6 interface dialer 1 Yeah, it's 1500 bytes. Okay, so interface dialer 1, IPv6, MTU, 1492. And we should see the OSPF v3 process now form an adjacency with router 4. Hopefully. Not sure why it wouldn't. Here's a question for you. What command can I type in to verify all the interfaces that OSPF is operational across? Let's do it for IP version 4 to start with. I want to verify that all my interfaces are actually running OSPF for IP version 4. Yeah, show IP OSPF interface brief. That's exactly right. So show IP OSPF interface brief. That's a great command. I mean, look at all the stuff it shows you. Not only can you spot, oh yeah, I'm missing an interface. Fast Ethernet 1.1 should be on there. So you could clearly see what's missing if something was, but also tells you what area the interface is in, and also tells you the network type, point to point, broadcast. Great. If you've learned any neighbors on that interface, fantastic command. Okay, so let's do IPv6 connectivity now. Show IPv6 OSPF neighbor. Router 2 has 3 neighbors. Great. That's what we want to see. Moving right along. Switch 2 has a single neighbor. That's good. That's what we want. Switch 3 has 4 neighbors. Let's see, 1, 2, 3, 4. Yep, that looks right. Now, router 4. We did some neighbor statements for IP version 4, but we didn't do any neighbor statements for IP version 6. And consequently, we haven't formed any OSPF v3 neighbors across our frame relay cloud. So we need to do that. Now this gets a little, these neighbor statements are just plain old nasty, because just like with EIGRP, OSPF forms a neighbor relationship with the link local address of your neighbor. So what I'm going to have to do is, first of all, look at my interface serial 10, where I've already written down the link local addresses of my neighbors. And now I'm going to have to create some neighbor statements for that. Yeah, now look at this. Why do you think the neighbor statement is not supported here under my OSPF process? It's not supported under the process, and yet it is supported under the interface. So why would the OSPF neighbor be under the interface here and not supported under the process? Because with IP version 4, you type your neighbor statement under your OSPF process. Well, here I think is the logic behind this. We know that when you configure a neighbor statement in OSPF version 3, you have to point to your neighbor's link local address. And with IP version 6, just like we saw previously, whenever I tried to ping the link local address of a directly connected neighbor, what happened? The ping would say, you got to tell me what interface to use to send this ping before I can do anything. Because it didn't know, it got confused, because every single interface with IPv6 on it starts out with FE80. So here's what I think. I think that the designers of this in the software, they had a choice. They could have kept the neighbor command under the process, but then they would have had to have added something. It would have been something like neighbor, the link local address, and then they would have also had to have included a field for you to put the interface, like neighbor FE80 blah 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 serial 0/0 or serial 0/1. So instead of doing that, they force you to put the neighbor command right under the interface itself. So there's no mistake, no way to get it wrong. So let's go ahead and do that. Do show run interface serial 1/0. Okay, IPv6 OSPF neighbor, and I want you to talk to this guy. And I want you to talk to this guy. Now with IPv4, just configure it on router 4 was enough for us to form a neighbor relationship with routers 1 and 3. And sure enough, it's good enough for OSPF version 3 as well. At least on one of them. We formed a neighbor with router 1. Still waiting to hear back from router 3. Still in the attempt state. Sometimes these things take a while. So while we're waiting, I'm going to go ahead and go over to router 1. Show run interface serial 1/0.134. Interface serial 1/0.134. IPv6 OSPF neighbor. And this, 131. This is the neighbor right here to connect him to router 3. Come on. Come on, router 3. What's going on with you? Let's go over to router 3. See if there's anything we can spot that's wrong on that router. Main thing I'm wondering about is, I'm pretty sure I put some frame relay maps in router 3 with link local addresses. But if I didn't, that would explain why nothing's working here. Yeah, I do. And let's just verify these. I just want to verify the DELCs. 341 and 131. Yep, this looks good. I've included OSPF in here. Okay, show IPv6 OSPF neighbor. Well, he's adjacent with router 1 across the point-to-point frame relay. Well, I could sit here and wait for a little bit longer, but I'm not going to do that. I'm just going to add some neighbor statements in this guy. Interface serial 0/0.134. IPv6 OSPF neighbor. I want you to talk to this guy. And I want you to talk to this guy. All right, that should be enough for these guys to start communicating across that non-broadcast multi-access link. Show IPv6 OSPF interface brief. Yep, it confirms here that I have activated it. It is in the correct area. Currently, there's no neighbors, though. Come on, you can do it. Show IPv6 OSPF neighbor. Is it possible that I have the wrong link local addresses? Show run interface serial 0/0.134. Ping. That's not good. Okay. I may have mismatched my link local addresses to my DELC numbers. Let's go back here. I already saved that, so I don't need that anymore. Okay, so we're in R3 right now. So R1, his link R1, his link local ends with EAB0. Here's EAB0. That's R1, and yes, 131 is the DELC to reach him. Okay. And router 4, his link local ends with 7AE0. Here's 7AE0. And yes, I use DELC 341 to reach him. So, what could be the matter? Let's see here. Let's go back to R1 and verify that his frame relay maps are correct. Okay, so on R1, to reach R3, R3 is 6DD8. Ah, missing a couple characters there. Somehow those got cut off. Well, that would explain it. I bet you the same thing happened on R4 as well. $6DD8, right? Yes. And then let's get rid of this other one. There it goes, comes right up. Okay, so this one is wrong. Okay, so that was the problem. Frame relay maps were wrong. And what about this guy? Show run interface serial 1/0. Yep, same thing here. And also the neighbor statement is missing those last. I wonder how that happened. That's really weird. 6D8. Okay. There we go. Show IPv6 OSPF neighbor. That's better. Good troubleshooting exercise though, wasn't it? Yeah, I like that. Okay, good. So now I should have end-to-end connectivity. Let's go back to router 2. And let's see here. We're looking for BB0B and BB0C. Those are the loopbacks on router 3. And here they are, 0B and 0C. And D and E are the loopbacks on router 1. And there they are. Okay. So far we've completed through H. Do you have any questions before I take a look at task I on this slide? Okay, so see here, ensure that router 2 can still ping the loopbacks of router 3 even if links connecting to subnet I are disabled. Actually, that's what we just did. The reason why this task is in here is because if we had not fixed the problems we had across the frame relay cloud, across subnet H, if those problems still existed and we still had no neighbors, let's bring up the topology diagram. So the problems I was dealing with were across this cloud right here. Right? And before I did, okay, which of the subnets in the topology will not elect an OSPF designated router? So go ahead and take a look at the diagram and tell me what you think. Will it be A, D, X, E, H? Which of those subnets will not have a designated router? Well, designated routers are only elected on two types of networks: broadcast networks and non-broadcast multi-access networks. Those are the types that have designated routers. So if we look at our topology diagram, let's draw some circles here around the networks that will have designated routers. So C, that's a broadcast network. D, we haven't configured X yet, so I'm not worried about that. G, E, those are all broadcast networks. Now F, that's kind of interesting. PPP over Ethernet. Do you think that's considered as a broadcast network or what? Well, it's PPP. I mean, OSPF sees it as PPP, so OSPF should view it as a point-to-point network. Let's see. And designated routers are not elected on point-to-point networks. So let's see here. Show IP OSPF interface dialer 1. Yep, network type point-to-point. So there won't be any designated router elected there. Okay, so most of these networks will have designated routers. The ones that will not are networks that are either point-to-point or loopback. So all of my loopbacks here, there won't be any designated routers on those. No DRs on those networks. There will not be a designated router on network F, because that's looked at as point-to-point. There will not be a designated router on network I, because that's using the point-to-point protocol, PPP, just regular PPP. And network J. Now let's check out network J, because we know that network J is going across a frame relay WAN. But the way it's been configured has been with sub-interfaces, and those sub-interfaces have been configured as point-to-point sub-interfaces. Now, we didn't actually go into those sub-interfaces and change the OSPF network type. So let's see if a point-to-point sub-interface is recognized by OSPF as an actual point-to-point network type. We'll go into router 1 here, show IP OSPF interface serial 1/0.132. And yep, it is point-to-point. So the answer to which networks will not have a designated router is A, B, F, these loopbacks here, this point-to-point network, and this point-to-point network. Those are the networks that will not have designated routers. Okay? Next question. What is the numerical type identifier, for example, type 1, type 2, etc., and the descriptive name of the LSA that will be in router 2's OSPF database describing the subnet mask used on links connecting to subnet E? Okay, so, oops. So we're talking about router 2, and here is subnet E right here. So what it's asking you is, think about what type of OSPF LSA, oops, don't want that. What type of OSPF LSA will be in router 2's database for him to learn about this network? Any idea? And specifically the LSA that will give the subnet mask of this network, right here. Well, both switch 3 and router 4 are connected to that. So switch 3 will generate a type 1 router LSA for this interface, and router 4 will create a type 1 router LSA for this interface. But because this is a broadcast network, because network E is a broadcast network type, neither one of these type 1 router LSAs will describe the subnet mask. In order to describe the subnet mask, it's actually going to be the type 2 LSA called the network LSA. The network LSA that's generated by router 4, that's the one that router 2 will have that will give the subnet mask of that network. Let's verify that. Okay, so let's go into router 2. Show IP OSPF database. We'll start at a high level and then we'll drill down a little bit. Show IP OSPF database. And we can see here that as far as router LSAs, okay, so these are all the router LSAs that he's got. So here's the router LSA that he got from switch 3. Here's the router LSA he got from router 4. And this is why we made the router IDs nice and easily visible. Okay, so let's start by looking at the router LSA from router 4. Show IP OSPF database. I specifically want to look at router LSAs from advertising router 4444. Okay, and here he says, okay, my name is 4444. Let me tell you about the links I have. He says, in area 0, I have 3 links. And here's his information about those 3 links. But the one we're concerned about, which is the 9.48, that's this one right here. No mention of a subnet mask. Not inside that type 1 router LSA. Similarly, if we did that same thing for switch 3, same thing right here. All he gives is his IP address. No mention of the subnet mask. So what we have to do is, now this tells us right here, this says, who is the designated router? Oh, it's switch 3. Switch 3 is the designated router. So therefore, I know that switch 3 is the one who needed to create the type 2 network LSA. So I can do show IP OSPF database network from the advertising router of .49. Uh-oh. Where's that? Oh, that's because I need to put in his router ID, not his IP address. That's the router ID of switch 3. There we go. So here he says, see, where's the one that we're looking for? Right here. This is the one. He says, okay, let me tell you, on this link I'm connected to, here's my address, and here's the network mask. So we can extrapolate from that because this is a host address, we can extrapolate from that that's in the 9.48 network because we've been given the subnet mask. So in a broadcast-based network or a non-broadcast multi-access network, it is the type 2 network LSA that contains the subnet mask information. All right, what about number C here? What is the same type of question as before? What is the numerical type identifier and name of the LSA that will be in Router 2's database describing the subnet mask for subnet J? Subnet J. So let's see, where is subnet J? That's way over here. Okay, so when we look in Router 2's OSPF database, what type of LSA will he have that gives him information about network J? Any ideas? Well, here's a big hint. Here's a big clue. Everything on this side, remember, was in area 0. And everything on this side was in area 1. At this point, if you can't figure out what type of LSA Router 2 will have about network J, you seriously need to restudy your OSPF. He's going to have that as a type 3 summary LSA. So our area border router right here, Router 4, he's going to advertise network J into area 1, into area 0 as a type 3 summary. So let's view that. Show IP OSPF database summary from the guy who advertised it, who is known as Router 4. And network J is the 9.60 network. And here it is. There is our network, 9.60. Okay. What will be the advertising router ID as displayed in Router 2's OSPF database in the LSA advertising subnet K? Subnet K. What do you think? So now we're talking about this subnet right here. And when we look in Router 2's database, who advertised that to him? The answer to that is Router 4. Once again, because Router 4 is the dividing line here between two areas, any of the networks over here in this area, Router 4 is the area border routers responsible for advertising that into area 0. So it will be his name on that LSA. Exactly. 4.4.4.4. Task number 4 here. Modify the OSPF router ID of Router 1 to be 111.111.111.111. You may not use the OSPF router ID command to do this. All right, so somebody tell me, what command or commands are we going to need to do to accomplish this task? Someone suggested maybe change the host name. No, not that easy. If we don't use the router ID command, how does OSPF normally pick a name for itself? How does OSPF normally come up with a router ID if you don't type in specifically a router ID? Well, first of all, it looks around at all of your interfaces and says, is there a loopback here? If there is a loopback, it says, is there more than one? If there is more than one, he says, okay, I'll pull the highest IP address from all my loopbacks, use that as my router ID. So if we go into router 1 and we add, now router 1, he already has 3 loopbacks. If we add a 4th loopback to him, giving him this IP address, do you think that's it? Is that all we need to do to get him to switch over to that as his new name? Well, let's find out. So we're talking about router 1. First of all, I have to get rid of the existing router ID command that's in there. Okay, so I got rid of it, and then I got this interesting message right here. Show IP OSPF. Oh, well, he's still using it, even though show run section OSPF. It's a lot of stuff in here, but keep going. There's no router ID in here anymore, and yet he's still using it. Okay, well, let me just go ahead and create the loopback anyway. Interface loopback, I've already got 0, 1, and 2, so let's do interface loopback 3. IP address 111, 111, 111, 111. We'll just make that a /32 because all we're doing is using that. Okay, loopbacks automatically come up. Okay, let's see. Let's see if he switched over to using that as his router ID. Nope. He's still using 1.1.1.1. Maybe if I clear his process, that will do it. Clear IP OSPF process. Now that killed all of his neighbor relationships, but they will come back. While they're coming back, now he's using this. Why did he use that? Because that's higher. That happens to be the IP address he has on loopback 1. And remember, it's the highest IP address from among all your loopbacks, and that is higher than 111, 111, 111, 111. So let's try something else. Let's try shutting down loopback 0 and loopback 1. Show IP interface brief. So in theory, if I shut down these 2 loopbacks right here, if they're down, oops, then these addresses should no longer be available as potential router IDs. Then he'll look at these 2 loopbacks, and he should use this one. However, as we saw, once OSPF picks a router ID, he really likes to stick with it. And so even now, even though that loopback is down, loopback 1, he's still keeping that as his name. So let's try clearing the process one more time. And now let's see if he switched over to that new loopback. No, he hasn't. Goodness gracious. Okay, so what else can we do? Show IP interface brief. Verify the loopbacks are indeed down. Yes, they're administratively down. At this point, the only thing we have, and this is a very extreme thing to do, but the only thing we can do is completely remove our OSPF configuration and reapply it. So I'm just going to do that to this. Let's go ahead and copy this first so I can paste it back in. So now at this point, all I have is my IPv6 OSPF configuration. See, IPv4 is gone. Now let's go ahead and copy that back in. Show IP OSPF. And now he's finally using that router ID that we want. Very painful process. So what's the moral of this story? The moral of this story is if you want a specific router ID, use the router ID command. Trying to manipulate loopbacks to get it so he uses a certain name is just really challenging. So here's what I'm going to do. So we've completed that task. I don't think we care about that at this point. Yeah, so let's go ahead and go back and do router OSPF1, router-ID, put it back to what it was. Interface loop 0, no shut. Interface loop 1, no shut. And clear IP OSPF process. I want to get him back to 1.1.1.1. Okay, now he's back to what he was before. All right, and step 5 here is our last OSPF task. Then we'll take a break. I know we're overdue for one. Modify OSPF on router 1 so that interface serial 1/0.34, that's the one going into network H, the non-broadcast multi-access network, is the only egress interface providing reachability to the loopback subnets on router 3. There should be no equal cost routing to these subnets for router 1. It says you may not disable any interfaces, you may not modify any interface characteristics that could influence other IP routing protocols. So, my question to you, how would you do this? So take a look at our diagram here just to bring this into focus. So right now we're talking about these loopbacks, and we're saying we want router 1 only to go out this way to reach those loopbacks. We do not want him to go out here. And yet we cannot disable this interface. We're not allowed to shut it down. And any commands that we might choose to do should not influence any other routing protocols. How do we do that? Okay, so Asif has an idea of, on serial 1/0.134, lowering the bandwidth to make it the more preferred interface. Everybody agree with that? I mean, that would work. That would accomplish what we want. The problem with doing that, Asif, is that even though it would accomplish what we're looking for, it would break this rule. Because if we start messing around with bandwidth, that's also possibly going to change EIGRP, quality of service, other things refer to the bandwidth of an interface as well. And we were told we're not supposed to change anything that might influence other protocols. Dwayne's got the right idea. Modify cost. Right? Go right to the interface and give it some artificial cost. All right, so let's take a look. Let's see here on router 1 right now. Let's see what cost values he's currently got. Show IP OSPF interface brief. Okay, so the non-broadcast multi-access interface has a cost of $781, and the point-to-point interface also has a cost of $781. So if we take this non-broadcast multi-access interface and we lower it, that should be enough. Let's see if we just lower it to 780, if that's enough to make it the preferred interface to reach those loopbacks on router 3. Okay, the moment of truth. It should be a pretty instantaneous change. Show IP route OSPF. And yep, there's the loopback 2 or network X, reachable via the non-broadcast multi-access. And here are the other 2, also reachable via the non-broadcast multi-access network H. So that worked. All right, so that concludes this section on OSPF. Okay, so in this next section, we're now going to be adding another layer or